Okay, so thank you very much for this opportunity. This is the last talk, so I will just try to be short. So I'm a PhD student from ISSP, and this is my professor, Masaki Yoshikawa. He really loves road bike. So today I'm going to talk about my research on 2D classical model with a TNR. It seems like many of the people here are using variational method instead of TNR. So at the end of this talk, I try to convince people that like TNR can do a little bit more. No, a little bit more, but TNR can do a lot of stuff. Just this. Okay, I can just do like this and. Oh, sorry. Oops. All right. I'll just go with this. Okay. So the reason why I started TNR when I started my graduate student is that a friend of mine told me like with a fixed point tensor of TNR, you can do basically anything for the critical system. What he meant by this is that you start from a tensor, local tensor that represent the local Boltzmann weight, and you do SVD and local entanglement filtering. You basically get the system size of square root of 2. And you do it over and over again, then you get the fixed point tensor as a converged tensor. Simple. And what you can do with a fixed point tensor is that you contract the fixed point tensor in the x direction, and you realize that this is kind of transfer matrix in y direction. And if you consider this part as a time-evolving MPO, okay, this lambda is nothing but the eigenvalue of the time evolution operator. So by mapping to 1 plus 1D, you realize that from the relation with a finite size CFT, you can calculate the scaling dimension of the theory. Can you use the pointer somewhere? Sorry. This one, okay, sorry. So this one, just taking the ratio of the fixed point tensor, you get the scaling dimension. Same for the central charge. Really great. And these things is tested in a lot of models, such as Eisen model. And for example, if you calculate the central charge after a certain RG step, you indeed see the convergence. And from this fixed point tensor, you calculate the scaling dimension of the Eisen model, CFT. And the good advantage of TNR here is that you can not only get the high precision for low-lying energy, but also for high energy part, you get great precision. But okay, this is a great story. But when I do it myself, I accidentally, or I believe it was a fixed point tensor, but when you renormalize again and again the fixed point tensor, you actually get some like it's not truly converging. This is because you have some sort of finite correlation length that is induced by finite bond dimension. And in this case, you need to some sort of define the reliable region that the numerical accuracy is guaranteed. And this is very, very important because some of the 2D classical critical system is exotic when the central charge is higher. So instead of focusing on what we can do with a fixed point tensor, my idea is what we can do with a finite size tensor, which is like this one, this one, this one, this one. What we can do. So today's talk is as follows. First, I'll introduce with a finite size tensor, you can compute the RG flow of the numerical to the system. And with that one, you can visually see the phase transition with a high precision. And then I move on to the quantitative analysis of the finite one-dimension effect. And then finally, this is why I came here. I am stuck with some new university classes that is really interesting. It has a peculiar central charge, but I would like to ask some questions for the CFT professionals. Okay, so let me start by defining the finite size scaling dimension. It is a straightforward by just redefining the dependence of L. And here I plot the finite scaling dimension along with the RG step for critical temperature with a low temperature and high temperature of the Eisen model for the magnetic operator. And what you see here, because this is nothing but the rescaled energy level, this going down means this sigma operator going down to the spontaneous symmetry breaking phase, which is like a twofold degeneracy. So by seeing this, by just plotting this, you see some sort of RG flow in the middle. So natural question is this finite size scaling dimension contains the RG information? So in order to tackle this problem analytically, what you need to do is RG theory. So in RG theory, what you have is a lattice model of the finite size system. And for the finite system sizes in the vicinity of criticality, what you have is CFT Hamiltonian plus some perturbation term. So this perturbation term, the important thing is relevant perturbation term, is that you start from here or here as an initial coupling, and when you increase the system sizes, you see the different flow of the coupling constants. And this plot of coupling constants for the various system sizes called RG flow. So this is what I want to do, just calculating the coupling constants for a given system size from the lattice Hamiltonian. So how do you do that? Actually, the deviation that we see from the previous slide contains the information about the coupling constants of the effective theory. How do you do that? It's easy. First, you start from the first order perturbation theory from the undergrad school. You have CFT plus some perturbation. And the energy shift is nothing but this one. Combined with the CFT, you get this equation. So I'll repeat the same procedure. We can calculate the RG flow as follows. First, you calculate the finite size scaling dimension from the ratio of the finite size tensor. And you plot it just like this. And you measure the difference from the CFT value. Then voila, you have GT, just the subtraction. So this is, if you do it for the magnetic field and the temperature slightly different from the critical temperature, you see RG flow. That is, the fixed point is located in center, and as you go for the RG step, you see this relevant RG flow from the center. Also, I would like to mention that using this method, finding transition temperature is easy. Just plotting the X sigma, for example, or a low-lying energy state in the vicinity of critical temperature. You just plot it for different system sizes. You linear fit. The crossing point is actually a phase transition point, and it's quite good precision. So there's no longer need for a Monte Carlo simulation to find the transition temperature. That's a simple one. I can go for a more complicated one, which is BKT transition. So BKT transition is described by a Sine-Gordon model, and Kosterlitz derived this famous Kosterlitz-Auger flow. And this, by solving this equation, you see this Kosterlitz-Auger flow, which is belong this BKT transition line. You have the phase transition into CQ1, Gaussian theory, and this disorder phase. So I applied the same thing. I don't explain the detail, but you can calculate the Auger from of the XY model as well. And you see the perfect matching of the Auger field theory. And just this is the plot that you just get it from the lattice model. So in this way, you can visually see the phase transition just by plotting. Also, one more thing is that if you look at the transition temperature, just by plotting, you see the 0.893. And this is currently one of the best accuracy for the phase transition temperature. Oh, okay. So this is the method that I introduced. So I'll move on to what can we do about this. With this method, we can actually do a quantitative analysis of the finite bond dimension effect. How much when did I stop? Okay, 15 minutes, okay. Yeah, it's gonna be fine, okay. So same for MPS and the TNR. We always have the problem with the critical temperature or critical parameter. And without finite bond dimension effect, for example, the calculated fine scaling dimension should converge to the CFT value. But when you calculate it, what you find is initially you start to converge. This is a bond dimension. Initially you start to converge, but at some length scale, you see some deviation from the critical value. Just like this. So I define this length scale as a kind of finite bond dimensional effect or correlation length that is caused by finite bond dimension. So for example, for this one, bond dimension 4, it diverges quickly. But when you rescale it, actually, so these things looks random, although when you rescale it with well-known correlation lengths, then all these lines collapse with each other. This means that TNR also has the same finite bond dimension effect as MPS. There's one more thing you can say is that this deviation from the CFT, this deviation, which is finite bond dimension effect, is proportional to L, which means this effect, this finite bond dimension effect, is effectively coming from the perturbation of the thermal operator. So this is a conjecture that in TNR, maybe in MPS as well, that as Andreas explained yesterday, that finite bond dimension effect can be considered as a perturbation by thermal operator. Thermal operator, I mean by the most relevant operator that is that respect the symmetry of the Hamiltonian. And this, by collapsing, we can see this finite bond dimension quantitatively. You can predict this. So by subtracting this, you can erase the finite bond dimension effect from the TNR. So what I would say is, as long as you have your MPS or tensor network has a symmetry, it keeps it, then this is the one. But in practice, you don't, for example, impose the symmetry. Then, for example, magnetic operator can appear. But the natural appearance I found from this model and Potts model is that there always thermal operator comes first, and then magnetic operator later. Yes. No, you mean this one? Okay. So this one. So, okay. For higher bond dimension, you see this convergence. But this, for finite bond dimension, you have deviation. And deviation is proportional to L in this log-log plot. And this is a kind of RG dimension, which is 2 minus XD. So if you see it, then it's 1. And in Eisen CFT, there's only one operator that has a scaling dimension 1, which is Stammer operator. You can do the same thing for a 3-step Potts model and other models like XY model. Then you see the RG scaling dimension of the thermal operator. Oh, could you ask again? Sorry. Mm-hmm. Oh, so this one, I'm looking at the difference between, like, it's kind of gap. I'm looking at the ground state energy and first excited energy. So I don't see the ground state scaling here. But I assume that the ground state scaling would be, I'm not sure. I can. Which one? Sorry, yeah. Mm-hmm.
The Casimir effect always has the same power law, so it's always 2, irrespective of the operator with which you perturb.
It's all the same.
The amplitude might be different, but the power is the same.
So
then, okay, sorry.
Okay, yeah, let me know later, maybe. Okay, I have 5 minutes. No? 20 minutes? Yeah. Oh, thank you. I appreciate that. Okay, but I will finish in 10 minutes or something. Try to. Okay. So this is a conjecture, and okay, finally I will go into interesting part to me, which is a kind of new series of university classes that is analogous to minimal theory. So this is everywhere in the CFD textbook, which is minimal theory. And the central charge is characterized by P and Q integer. And for form-free Eisen model, critical model, three-step model, and most importantly, when you go for higher, then you get XY model. So this is a discrete series of CFDs which converges to C=1. So what you can do is you can think of a CFD series that is convergent to C=2. And you can describe this series by this Hamiltonian, classically, on square lattice. And when you think of this one, the first thing that you might think is a Heisenberg model, of course. And the Heisenberg model has a phase transition at t=0, which is a spontaneous symmetry breaking. And around this alignment, you have basically two goldstone bottom. So you have t=2. This is the limit. And the other limit, you can think, is Eisen model. So on the sphere, you introduce some sort of anisotropy, then you get the Eisen model. And what I mean by series is that you can go little by little to find this series of regular polyhedron, which all of which has a spontaneous symmetry breaking. And what I found interesting is that the only criticality that is known is Eisen model, Heisenberg model. This is four-step Potts model. And this one is 3 times Eisen model. And these three is not known, even though it is super simple model. And there are only a few previous work. I think I counted like 5. And one of them, the newest one, is from a group of Nishino or other people. And I got to know this model because these 2 people just texted me. And like, can you do it with a TNR? And their method was corner transfer matrix. And basically, you measure this central charge with a kind of entanglement entropy scaling. The result that they found is a little bit peculiar when you consider them as a kind of rational CFT. These things are not intuitive. So I calculated the same model again with the same method, then I got this. Okay, so first thing is that this one, although for octahedron, so this is octahedron, tetrahedron, cube, icosahedron, and dodecahedron. And for octahedron, even though I write 1.25, it was first order phase transition. I confirmed it, but in the middle phase, you see some sort of crossover to 1.25, which I think is reasonable to think that like it's a crossover from chiral Potts model. But for the dodecahedron model and icosahedron model, you see this intriguing central charge, which is 1.7 and 1.75. And I tried to find the literature everywhere, but I can't find it. So if you know it, tell me. And I thought I had no time, so I skipped the details. But basically, I can I already calculated the scaling dimension. I already calculated the OPE, calculated the like a structure, like a thermal operator. You can also calculate the scaling dimension of the thermal operator. But then I found that this model is indeed described by a deformation of the O3 model plus some spin 6 perturbation, which is the first spin. Why is the reason why it's spin 6 is that so these two model has a A5 symmetry. It's hard to explain intuitively, but these two has a same symmetry, A5 symmetry, and these two models are dual in a way that if you put vertex on the center of the surface, you get this model. So they have the same symmetry, and this A5 symmetry has trivial representation only at spin 6. That's why. So what you find is that this scaling dimension also follows the A5 symmetry, and you see like you start from ground state L equals 0, 3-fold degeneracy, 5-fold degeneracy, and 7-fold degeneracy is breaking into two parts because of this spin 6 invariant term. And these things are, the sign is different because of the duality. Okay, it's time okay? So this is a summary. I am sorry that I didn't explain well, or maybe I skipped some part, but the main message is that with TNR, you don't even need to go to fixed point. You just calculate the few steps and you see the phase transition and RG flow. And then you can also do some sort of finite entanglement scheduling, and you can treat some sort of finite bond dimension quantitatively. And finally, I don't know this university class, help me. Thank you.